Hi, in this video, we want to take a look at rank-based statistics in non-parametric statistics. All right, so the big idea here is that I want to run statistics just like I would with all the other videos that we've talked about up to this point. But there's a problem. When I check the distribution assumptions, they don't hold. It doesn't work out. All right, so then what am I going to do? My statistics professors kept on saying, make sure you check the assumptions, and the assumptions don't hold. Well, now I need to figure something out to do. One thing I could do is throw my hands up. Oh, I can't do that. Can't do anything with this. But I'm not going to get paid. Right? We do statistics for money. So we're going to have non-parametric statistics come to the rescue. Non-parametric statistics, what they're going to do is that we are going to convert our data to the rank of the data. So our lowest observation will be switched to 1. Our second lowest observation will be switched to 2. Our third lowest observation will be switched to 3, and so on. All right. And so then what I'm going to do is I'm going to run statistics on that. What we're going to do now, instead of having like normal distribution or binomial distribution or something like that, we're going to say, hey, I'm going to work with uniform distribution of the numbers 1 through n. And I'm going to use that new distribution as the way that I get my p-values and run my analysis. All right, so rank-based statistics, also known as non-parametric, are procedures that are based on the rank of the data rather than the actual observed values. These tests make minimum assumptions about the underlying distribution of the data, making them ideal for situations where the data does not conform to the assumptions required for our test. All right, so like when you hear me say normally distributed, equal variance, stuff like that, if that doesn't hold for my data, then I have this alternative of non-parametric statistics. Now, here are probably the 3 most common non-parametric statistics to run: the Mann-Whitney U-test, the Wilcoxon-Signed-Rank test, and then Kruskal-Wallis H-test. So Mann-Whitney U, this is used to compare 2 independent samples to determine if there is a significant difference in their distributions. The null hypothesis is that the distributions of both groups are equal. For Wilcoxon-Signed-Rank, this test is used to compare 2 related samples or repeated measurements on a single sample to assess whether the population mean ranks differ. And then for Kruskal-Wallis, this is used to compare more than 2 independent samples to determine if there's a significant difference in their distribution. This is the non-parametric version of ANOVA. Rank-based tests offer several advantages, including robustness to outliers and their ability to handle ordinal data. However, these tests also have less statistical power than parametric tests when the assumptions of the parametric tests are met. Additionally, they may yield ambiguous results when there are many tied ranks. All right, so one of the major problems with non-parametric tests is that I'm not taking full advantage of my data. All right, so if I know, let's say that I knew my data was normally distributed, but I went ahead and ran non-parametric tests on it. Well, I'm not using the precise presentation of my data. I'm not using the full effect of it. And so I'm going to have less precise results. And that's where the less statistical power comes into play. So if I use a non-parametric test, in general, we're going to be more likely to fail to reject the null hypothesis than if we were using a parametric test. Also, when there's ties, we have to make a decision on what to do. And if you choose one method and I choose another, we can get different results. So there's some ambiguity in it. All right, so let's talk some more about advantages and disadvantages of rank-based statistics. In general, we don't use these if it looks like the parametric test is valid for our data. All right, so here are the advantages. First and foremost, we have fewer assumptions. That let's say that I don't even have time to check my assumptions. Maybe I don't really understand what the assumptions are. Maybe the assumptions would be violated for parametric statistics. Then I can move over to rank-based statistics and run with things. And we have, we'll be, we have a solid framework for proceeding. So rank-based statistics do not need to worry about the distribution of the data, that is normality nor equal variances. So rank-based statistics make fewer assumptions about the nature of the data, and this offers more flexibility, and you really can handle a wider range of situations than parametric statistics. Rank-based tests are resistant against outliers. So by converting our smallest value to 1, our largest value to n, I've muted the outlier aspect. And so rank-based statistics are less affected by outliers. And so this, can be a huge advantage if I have, outliers flowing around. Now, parametric statistics can't handle ordinal data. So if I have first place, second place, third place, or if I have high, medium, low, or let's say, number of stars rankings on a website, that is ordinal data. And so the methods that we've talked about previously can't handle this. And so we need an alternative. We can go to rank-based tests. And then we're also resistant to heteroscedasticity. So non-parametric tests are more robust to heteroscedasticity. That is where we have different variances for different subgroups. Now, disadvantages. And the first one is a big one, less power. All right, so I'm less likely to reject the null hypothesis when I'm running non-parametric statistics. We have ambiguity with tied ranks. So if we have a tie, I have to make a choice on how I'm going to handle that. We could say we take the average of the ranks. We could do a random selection. We could say all of the ties get the smallest corresponding rank. All of them get the largest. We have to make a choice on how we handle this. We have limitations when we're dealing with interval or ratio data. So rank-based statistics are excellent for ordinal data, but they don't fully use the information we have available when we have numeric data. So if I have normally distributed data, really, I don't want to use non-parametric tests because I'm not utilizing the full information I have about my data. Also, it can be harder to interpret at times. Parametric tests, they were built up looking at mean and variance, which correspond to the first and second moments in physics. There's more of an interpretation aspect. Central tendency, for the mean, it connects to like central, the center waypoint on a physical object. There's more interpretation that we can have here. Well, non-parametric tests, it gets a little bit harder to figure out what's going on. And also, non-parametric tests can have some pretty complicated formulas, and they can have different presentations. So the same formula could be easier in one presentation for interpretation as humans. Another presentation could be easier for calculating by hand, and another one could be better for calculating by the computer. And so when I go looking at formulas, I don't know which one is getting printed on the page for me. All right, so now let's talk about different tests, and let's take the parametric test and its corresponding non-parametric tests. So we have a t-test for independent samples. So we're checking to see if we have different means of two different groups that corresponds to Mann-Whitney U. We have paired t-test. This is Wilcoxon-Simes rank test. One-way ANOVA corresponds to Kruskal-Wallis. Two-way ANOVA is Friedman test. Pearson correlation, we can go with Spearman or Kendall Tau. I prefer Spearman personally. Simple linear regression, we have a non-parametric version. And for multiple linear regression, we have rank-based multiple regression. And so each pair in the table is generally used in similar situations or to test similar hypotheses. It's not exactly a one-to-one because, like for the parametric test, I'll be checking the mean, while the non-parametric test, I'm checking the median. And so they correspond in that they're in a more general sense. The tests on the right-hand column make fewer assumptions about the data and are based on ranks rather than the raw value of the data. All right, so let's talk about the hypotheses and assumptions of each of these tests. And so Mann-Whitney U, here, our null hypothesis that the distribution of our groups are equal, so that there is a 50% probability that the observations from a value randomly selected from the population exceeds an observation randomly selected from another population. Alternative hypothesis is that the distributions of both groups are not equal. Now, our assumptions are that we have independence of observations, we have ordinal, interval, or ratio data, and the shapes of the two distributions are identical. This really is a low bar to achieve. Now, Wilcoxon signed rank test, our null hypothesis is that the median of the differences between pairs of observations is 0. The alternative is that the median of the differences between the pairs of the observations is not 0. Our assumption is that the differences are symmetrically shaped around the median, and the observations are paired and come from the same population. Each pair is chosen randomly and identically. Now for Kruskal-Wallis, remember this is the non-parametric version of ANOVA, one-way ANOVA. The null hypothesis is that all of the medians for each subgroup are equal. So remember that in one-way ANOVA, it was mean that we were interested. Now we're interested in median. Alternative hypothesis is that at least one population median of a group is different from another. The assumptions are that all groups are identical in distribution except for the median. All responses are independent, and the data is at least ordinal. Now for Friedman's test, our null hypothesis is that the medians of the treatments as groups are all equal. Alternative hypothesis is that at least one treatment has a different mean, and our assumptions are the observations are independent, the dependent variable is at least ordinal, and the blocks are mutually exclusive and exhaustive. Now for correlation, we have Spearman and Kindle's tau. Both have a null hypothesis that the variables are independent. The alternative hypothesis is that the variables are not independent. That is to say, they are correlated. And the data needs to be at least ordinal, and the observations are independent. Now for the simple linear regression non-parametric version, our null hypothesis is that there's no monotonic trend between the two variables. Alternative is that there is a monotonic trend between the two variables. And we assume that the data is continuous. The relationship between the variables is monotonic, and the observations are independent. Now for rank-based multiple regression, our null hypothesis is that the median of all the groups defined by the combination of categories of the independent variables are the same. The alternative is that at least one median is different from at least one other median. Our assumptions are that we have independent observations, and the dependent variable is at least ordinal. All right, so now here, let's just talk about how to execute in R. All right, so I'm going to run through a whole bunch of examples using the MT-CARS dataset. So for Mann-Whitney U, something that's interesting when I want Mann-Whitney U, I actually run the Wilcox.test. And notice that Wilcoxon is misspelled. Statisticians know Wilcoxon is misspelled in this function. It got set up that way. Nobody's fixed it. But Mann-Whitney U, actually, to run it in R, we use the Wilcox.test. If I want to do Wilcoxon signed rank test, I use the exact same function, but here I specify that they're paired. For Kruskal-Wallis, I run something very similar to ANOVA, but I go Kruskal.test. for Friedman, all right, so we have to have multiple, we want multiple observations for each of the subgroups that we have for all the different combinations. Here, to be able to actually run the code, I need to first aggregate by the subgroups, and then I'm using the mean to aggregate. And so then I can run my test. If I don't do the aggregation, the code the function isn't going to run. And for Spearman and Kendall correlation, I use the same function that I did for Pearson correlation, but now I specify that the method is different. Kendall's tau tends to take longer to compute than Pearson and Spearman. Pearson is by far the fastest. Spearman, you can look at it as converting your data to rank, then running Pearson correlation. Now, the non-parametric version of simple linear regression. Here, this is in a special package, the MBLM package, and we use the same function, the namesake function, to run this. I give a formula and a data set, and it gives me my equation. And we can also do something that looks a lot like multiple linear regression, but it's fitted using a different method. We're going to use the rfit package, use the rfit function, same namesake, and we can see we have something that looks a lot like a regular linear regression model. So in conclusion, the rank-based tests, often referred to as non-parametric tests, are robust and versatile tools for statistics, especially when our assumptions for parametric tests are not met. The heavy hitters for non-parametric statistics is Mann-Whitney U, Wilcoxon-Signed rank, Kruskal-Wallis, Friedman, Spearman, Kendall's tau, and then the non-parametric versions of regression. And typically, we're using ranks rather than the raw values when we do this. The advantage here is that we don't have assumptions, or as many assumptions, and we're less sensitive to outliers, and we're able to handle a wider range of data type. However, while these tests have several advantages, there are certain problems or lackings that come up. So we have less statistical power. That means that we're more likely to fail to reject the null hypothesis just coming out the gate than the parametric counterparts, because we're not taking full advantage of our data when we do this conversion. Also, the formulas can be pretty complicated and can be hard to interpret what's going on. Also, we have to deal with ties when we deal with non-parametric statistics. And so how you choose to deal with ties and how I choose to deal with ties can give different results. The typical way of going is just give the average. So if let's say the 5th and the 6th value are equal to each other, so I could do 5.5. I could make both of them 5, make both of them 6, or I could just randomly pick which one's 5, which one's 6. All 4 of those have their merits. There's advantages and disadvantages. We have to choose. I pick one way, you pick another. We can get different results. All right, well, that's all I've got for you. Life is short. Do math.